Good evening, everyone. My name is Janelle Gurley, and I am the Director of Science and Programs at Murray Mitchell Association of Nantucket. And it is my esteemed pleasure to welcome Dr. McKinley Brumback for this evening's Science Speaker Series presentation, which has been generously made possible by our lead sponsor, Bank of America, as well as our additional sponsors, the White Elephant Hotels and Resorts of Nantucket and Cisco Brewers of Nantucket. And before I hand it over to Dr. Brumback, I'd like to share a little bit on what she will be presenting this evening. Her featured presentation, Using X-rays to Probe the Universe's Strongest Magnetic Fields. High-energy astrophysics tests our understanding of fundamental physics in the most extreme environments in the universe. Among these are neutron stars, which host the universe's most powerful magnetic fields. These fields are impossible to reproduce in Earth-based laboratories, but observational astrophysics offers a direct way to investigate these environments. Brumback works with systems called X-ray binaries, in which gas donated by a stellar companion moves towards the neutron star and becomes increasingly hot until it emits X-rays. Eventually, the magnetic force becomes much stronger than the gravitational force, and the gas is funneled onto the magnetic poles of the neutron star. Dr. Brumback is interested in studying the shape and movement of gas in this region, where the gas flow transitions from gravitationally dominated to magnetically dominated. By using X-ray observations from different NASA missions, these regions can be studied, and the shape of the gas as it moves around the neutron star can be mapped. And to share a brief bio on Dr. Brumback, Professor McKinley Brumback is an astronomer who studies X-rays coming from some of the most energetic and extreme environments in the universe. She uses observations from NASA and ESA X-ray observatories to investigate how matter behaves close to neutron stars, the ultra-dense and magnetic objects left behind by massive stars. Brumback is an assistant professor in the Department of Physics and Astronomy at Dartmouth College in 2020, and let me rephrase, I skipped ahead a line. Currently, Dr. Brumback is the assistant professor in the Department of Physics at Middlebury College in Middlebury, and she completed her PhD in Physics and Astronomy at Dartmouth College in 2020. After graduation, she continued her X-ray astronomy research with postdoctoral positions at the California Institute of Technology and the University of Michigan. I got really excited to introduce her, so that's why I skipped ahead. But everyone, please help me welcome Dr. Brumback this evening, who it is such a pleasure to host. Welcome, McKinley. How are you?
Well, I'm doing great. Thank you so much, Janelle, for the kind introduction, and thank you for the invitation to be here. It's really wonderful to get to share my research with all of you.
Well, we are very excited for the journey that you are about to have us embark on. So whenever you are ready, I will stop sharing and you have full control. Welcome.
Thank you. Okay, let me share my screen and start the slides. How does that look?
Looks amazing.
Perfect. Okay. Well, I'll dive right in. Thank you, everyone, for coming this evening. I'm excited to share my work with you, probing the universe's strongest magnetic fields with neutron stars. None of this work would be possible without my wonderful collaborators. I collaborate with a great group of X-ray scientists who study neutron stars right along with me. And I'd like to particularly thank my mentors, Ryan Hickox, Fiona Harrison, and John Miller, who have guided me throughout my research and throughout my academic journey. Speaking of that academic journey, I often get asked how I ended up doing X-ray research, how I ended up at Middlebury. So I'd like to start with just a brief introduction to my research path and what brought me here to Middlebury. I started as an undergraduate at Hamilton College, that's in upstate New York, a small liberal arts school. I was a physics major, but I minored in education studies and mathematics, and I was very interested in being a teacher. That was my prime career goal. And to this end, I participated in a lot of demo teaching at our local school, the Clinton Middle School. And so here I am doing a demonstration about forces and pressure by using a sledgehammer to smash a cinder block on the principal of the school while he is lying on a bed of nails, all to demonstrate that the pressure is low enough as it distributes the force over this large area. All this teaching experience that I gained as part of my education studies minor really gave me the goal of becoming an astronomy professor and being able to teach this at the college level. So after undergraduate, I decided that I wanted to pursue graduate school, and I did that at Dartmouth College in Hanover, New Hampshire. I worked with Professor Ryan Hickox, who first introduced me to X-ray astronomy and to neutron stars, and I continued my interest in teaching as a teaching assistant, doing astronomy outreach and those kinds of things. I graduated from Dartmouth in 2020 during the pandemic, the height of the pandemic, and so this is the only picture I have from my graduation, 6 feet apart with my thesis advisor, Ryan Hickox, but nonetheless very proud to have graduated. And after Dartmouth, I went to my first postdoctoral position at Caltech. These postdoctoral positions are research positions after your PhD, where you get to deepen your research and expand the amount of science you get to do. I was very lucky to go to Caltech and work with Professor Harrison. She is the PI of the NASA New Star mission, which is an X-ray mission I will talk a lot about in my research talk today. And so being able to work directly with her was an absolute dream come true. I also continued my interest in teaching. I mentored undergraduates in summer research projects while I was at Caltech. My second postdoc was at the University of Michigan. I worked with Professor John Miller, who's an expert in X-ray spectroscopy for objects like neutron stars. I also got the opportunity to teach a full course to University of Michigan students, which was really, really incredible and helped give me even more teaching. This culminated finally in my current position at Middlebury College as an assistant professor of physics. I just started this summer. I'm currently teaching Introduction to the Universe, which is a wide look at introductory astronomy from an algebra perspective. And it's a really exciting class. I'm really enjoying it, and I hope that my students are as well. And here's one last robe picture. This is me in front of Middlebury's physics building. You can see the dome in the background of our Middleman Observatory on the roof of our science building on the day that we welcomed our new freshman class to campus this fall. So that's my research path, and I'd like to jump into my outline of the research talk for now. I envision this having 4 main parts. I'm going to introduce to you what neutron stars are and why their environments are so extreme and unique and what we can learn from studying them. I'm then going to introduce X-ray telescopes and why studying these sources in the X-ray is particularly interesting and particularly powerful. I'll then go into great detail about one of the projects that I've done where I actually map the shape of gas in disks around these sources. And I'll end with hinting at some future research that I hope to do, an interesting place where I think this research can take us in the future. So jumping right in with an introduction to neutron stars, what is a neutron star? Well, neutron stars are called stellar remnants. This is because they're formed inside stars and left behind after a star lives its normal lifetime. When we have massive stars, stars that are several times more massive than the sun, they go through processes of nuclear fusion that allow them to fuse elements, lighter elements like hydrogen, helium, etc., into heavier elements like carbon, nitrogen, all the way up to iron. When the fusion of iron happens, this process no longer releases energy, which is how stars shine through fusion, the release of energy. The fusion of iron actually consumes energy. So when a star actually fuses iron in its core, it now essentially consumes itself. There's no more radiation being emitted from the star. There's nothing left to hold up its surface. And so it goes through a runaway gravitational collapse where the entire mass of the star implodes inwards towards the core. The core is compressed. It experiences a huge amount of pressure from all of this gas rushing inward. And the inner core is then formed much more densely as the outer layers of gas rebound against it and explode out into space. We know this energetic process as a supernova explosion, and we see them from high mass stars. What's left behind after a supernova explosion is a type of compact object. One of which is a neutron star, or it could be a black hole. So let's talk a little bit more about what these compact objects are and the different flavors of them. Now, in reality, there are 3 flavors of compact objects, but the first one, white dwarfs, are not formed through the process I just described, the supernova process. These are formed by low-mass stars. And what happens is that still inside of low-mass stars, the center of the star is experiencing high pressure from the weight of all of the gas in the star pushing down on it. This is the same phenomenon as when you dive to the bottom of the pool and your ears hurt. There's a lot of water above you, and so you're experiencing higher pressure. The same thing is true in stars, but to a much higher degree. The interior of the star is undergoing extreme pressure. The pressure is so high that it starts to push atoms together. But atoms contain electrons in their outer orbits, and electrons all have negative charges. And per the laws of electrostatics, electrons do not like to be put into the same place. They actually repel each other and try to not occupy the same space at the same time. This creates an outward pushing force against the inward force of gravity trying to condense all of the material together. This is called the electron degeneracy pressure, and it is what forms a compact object called a white dwarf, which will form from low-mass stars. The exact same process applies to our high-mass stars and their supernova explosions, except again, everything is kind of heightened because we have more mass and so a stronger force of gravity. During these supernova explosions, when the entire star is collapsing down, the electron degeneracy pressure can be completely overwhelmed. The electrons are pushed together, whether they like it or not. What's left then to kind of halt this collapse of all of this gas crushing down is neutron degeneracy pressure. It's the exact same force. The neutrons do not want to occupy the same place at the same time, so they resist being pushed together and create a repulsive force. If the star is in the right mass range where this inward collapse can be stopped by neutron degeneracy pressure, then what we have left is a neutron star. If the gravitational collapse cannot be halted by neutron degeneracy pressure, if the star was so massive that the force of gravity is so great that it overcomes this neutron degeneracy pressure, then the entire mass collapses to a single point and forms what we know of as a black hole. And so these compact objects involve types of matter that we don't naturally find on Earth. This matter is very dense, and it can have really strong magnetic properties in some cases. In general, as we move from white dwarf to black hole, we're experiencing stronger and stronger forces of gravity from these compact objects because more and more material is being crushed into a small area. That gives us a strong gravitational force. That gravitational force means that these objects are quite small, they're compact. So as the gravity increases, the size also decreases. So white dwarfs are larger than neutron stars, which are larger than black holes, which we believe just occupy a single point in space. These compact objects are some of the most interesting objects in the universe, but they're hard to study because they are so small, because they have such small radii. We only have a couple direct images of these types of objects. On the left here is a Hubble image of Sirius A. Sirius is the brightest star in the night sky, viewable in the northern hemisphere in the winter. And if you get a telescope or a strong pair of binoculars and look at Sirius, you might notice that it has a very small, very faint companion. This is Sirius B, and Sirius B is a white dwarf, and one of the few that is close enough that we can actually image it. And you can see in this image just how much smaller than the regular star, Sirius A, Sirius B, the white dwarf, is. One of the only places in which we have actually directly seen a neutron star is within the remnants of these supernova explosions that create them. So the image on the right is a multi-layered image of the Cassiopeia A supernova remnant, the most recent star to explode within our galaxy. And at the very center, marked with the arrow, is an incredibly tiny white point, and that is the neutron star left behind by the explosion. But in general, we don't get to see these sources directly. We have to use other methods to study them. Now, my research focuses on neutron stars, so I want to put these incredible objects a little bit into perspective for all of you. Neutron stars have a typical diameter of about 20 kilometers, which translates to about 13 miles. And in case you need a reference, something close to home for how big that is, well, the island of Nantucket is about 14 miles wide at its widest point. So essentially, a neutron star could fit on Nantucket, or at least on its diameter. This is an incredibly small object. When we think of objects in outer space, we often think of very big ones, but neutron stars are very small because they are made of this degenerate compact matter. Within this tiny area is the mass of 1.5 times the mass of the sun. This is what I mean when I say that the material is so dense. It doesn't function like material we find here on Earth. The entire thing has the density of the atomic nucleus, essentially meaning that if you could travel to a neutron star, pick up a teaspoonful of that material and bring it back to Earth, that material, that teaspoon, would weigh trillions and trillions of pounds just because the material is so dense. This density, all of this mass in such a small area, gives neutron stars incredibly strong gravitational fields. But actually, their most extreme feature is not their gravitational fields, it's their magnetic fields. So a neutron star's typical magnetic field can be up to 10 to the 12 Gauss, where Gauss is a unit of magnetic field strength measurement. And in case you've never encountered the unit of Gauss before, well, Earth has a magnetic field, which you might have experienced by using a compass, and which ships and planes use to navigate across Earth, and that is 0.3 Gauss. So the magnetic field of a neutron star is completely beyond any magnetic field that we've ever experienced on Earth. And in fact, it's so strong that we don't know how to create such a strong magnetic field in a laboratory, and even if we did, it would be highly unsafe to do so. The only place where we can experience these magnetic fields and study how they affect the environment around them is where they naturally occur in space in neutron stars. And they are some of the most extreme environments found in the universe, perfect test beds for our understanding of the laws of physics, if we really know what we're talking about when we're talking about particle physics and gravity and relativity, all these big, big topics. So where do we find these neutron stars to study their magnetic fields? Well, they can often be found in binaries, and this is where I like to study these sources. When neutron stars are found in binaries, this means they have a lot of gas around them that ends up getting quite hot, so they emit X-rays. So these types of objects are called X-ray binaries. Let's walk through what the anatomy of a typical X-ray binary looks like. An X-ray binary consists of a companion star, which is just a normal star undergoing nuclear fusion. It can be a high mass star, it can be a low mass star, it doesn't really matter. But either way, stars tend to transfer their material off of their surfaces. High mass stars are incredibly bright and they're constantly shedding their outer layers of gas. And low mass stars, when they form in binaries, can also gravitationally share gas to a companion. So we have a normal star that is transferring some mass gravitationally, shedding its gas, and that gas can now fall onto the neutron star. When this gas is falling towards the neutron star, it forms a spiral where it spirals in closer and closer and closer until it eventually hits the neutron star surface. And all of this gas streaming in and spiraling in at once forms a disk, which we call an accretion disk. Accretion is an astronomy term, which essentially just means an object is pulling gas towards it under the influence of gravity. So the accretion disk is the disk of gas that is falling towards the neutron star. As it falls towards the neutron star, it gets incredibly hot. It's losing a lot of gravitational potential energy. The gas is getting denser and frictionally heating itself. It gets hotter and hotter as you approach the neutron star, until the point that the innermost ring of gas is emitting X-ray light. And at the very center is our neutron star pulling in all of this gas from its companion. And I'm most interested in what happens at the very center of these systems. So let's zoom in and look at what happens there. As gas falls down towards the neutron star, as I mentioned, it's getting hotter. When gas gets hot, it enters a state called ionized. This is where the gas has, the individual atoms have lost their electrons. They've been hit off by high energy photons, and so the remaining gas is positively charged. So we have positively charged, very hot gas falling towards an extremely strong magnetic field. And electromagnetic forces tell us that charged particles, like ionized gas, cannot cross magnetic field lines. It needs to flow along magnetic field lines. So when this hot charged gas arrives at the radius of the magnetosphere, the area of the magnetic field of these neutron stars, 10 to the 12 Gauss, the magnetic field cuts off the disk. We call this truncating the disk at some radius away from the neutron star. And that's what's seen in this artist's rendition here. The radius at which the disk is truncated is the radius of the magnetosphere, where the magnetic field really takes over. Once the magnetic field takes over, our typical understanding of accretion as being governed by gravity and Newton's laws of gravity goes completely out the window, and we enter magnetically dominated accretion. Here are some models from real papers that have been trying to model the complexity of this system that suggest what this might look like. When gas hits the magnetic field, it follows along the magnetic field lines to the north and south magnetic pole of the neutron star and essentially funnels along the field lines and dumps directly onto these magnetic poles. These arcing streams of material that carry gas from the disk onto the neutron star are called accretion streams or accretion columns. And here the gas is locked to these magnetic field lines and just dumping onto the poles of the neutron star. This trapped gas in the magnetic field is incredibly bright. It's emitting a large amount of X-rays and accelerating particles up along the field lines as well out into space. Here's a video from the JPL laboratory of NASA that kind of indicates what this system might look like. We have the dark red accretion disk with the bright blue neutron star at the center. And we see the accretion streams, the accretion columns arcing off the disk and dumping onto the magnetic poles of the neutron star. And every time that pole points towards us as the neutron star spins on its axis, we see a bright flash of X-ray light. This is essentially a lighthouse. It is rotating around, shooting out beams of X-ray radiation. And when those beams intersect our line of sight here on Earth, we see an X-ray flash. So pulsars are just X-ray lighthouses waiting to be studied. How do we go about studying these X-ray lighthouses emitting this incredible amount of X-ray radiation in space? Well, to understand that, I'd like to tell you a little bit about how X-ray telescopes work. This is the second part of my talk. There are many different types of X-ray telescopes that specialize in different types of studies. So I'm speaking kind of generally about X-ray telescopes here. Each telescope is a little bit specialized. You can see that in these diagram renditions of XMM Newton, which is a European Space Agency X-ray telescope, and NuSTAR, which is a NASA X-ray telescope, both of which I've used in my studies of neutron stars. They have very different builds. You can tell that they look very different visually, and this is based on what they are designed to do. XMM Newton is sensitive to lower energy X-rays, and NuSTAR is sensitive to higher energy X-rays. So in order to understand how X-ray telescopes work, I'm going to frame this in a direct comparison to how optical telescopes work, since this is a system that people usually have seen before or might have some familiarity with. An optical telescope, such as the telescopes we have on the roof at our science building in Middlebury, the Middleman Observatory, functions with a parabolic primary mirror. That's what's shown in blue. This parabolic mirror will catch incoming light rays, send them to a secondary mirror that's shown in yellow, and that secondary mirror focuses the light at a focus point, that's the X, outside of the telescope. What I want you to notice from this typical design, this is a Cassegrain telescope design and is one of the most common ones used. Hubble is a Cassegrain telescope, for example, is the angle at which the light rays, the black lines, are impacting the telescope. The light rays are coming in at very large angles and bouncing off of the primary mirror at very large angles. However, we know that X-rays don't behave like this. This is why X-rays are great for medical imaging. X-rays tend not to bounce right off or reflect off of surfaces. They tend to pass through. This is great if we're a doctor looking at bones, but if we're actually trying to collect these X-rays and study them like an X-ray astronomer, it makes things very challenging. So X-ray telescopes don't function like optical telescopes. They're actually called grazing incidence telescopes. And what this means is that the angle at which the photons, these X-ray photons, come in and strike the mirror, it needs to be a very small angle. We're kind of gently coaxing the X-rays into a focus point by bouncing them off many, many small angled mirrors and sending them to a focus point. This mirror then can be used to actually capture and focus X-rays. So another big difference between the optical and the X-ray telescopes is how we make them more powerful. When we want more power from a telescope, it essentially means we want to capture more photons. And if we have a circular or parabolic mirror, like we do with optical telescopes, all we need is to increase the mirror diameter to make the mirror larger, and then we will catch more photons and we will have a more powerful telescope. With the X-ray mirror, making the radius of this mirror larger isn't necessarily going to catch us many more photons. Instead, what we can do is we can nest mirrors inside of each other like shells or like rings on a tree. So here's what I mean. Here are two examples of actual mirrors that do this. On the left is the mirror from SOFIA, an optical and infrared telescope, where we just have a circular parabolic mirror capturing a large amount of light. On the right is the mirror from XMM Newton, which looks solid, but if you look closely, you'll see that it's faintly grooved. These are the nested mirrors all within this large housing, holding them to be able to catch X-rays at these really small angles. It's absolutely incredible that we're able to do this and able to catch these X-rays in this way. Some other key differences between optical and X-ray telescopes, not only is it their technology and how they actually capture these photons, it's how they function. In terms of location, we can place an optical telescope either on Earth's surface on the ground or in space like the Hubble Space Telescope. And getting in space is great because it means that we don't have to look through the atmosphere, which is very dirty and very turbulent and can introduce a lot of noise into data. X-rays, however, do not penetrate Earth's atmosphere very well. The atmosphere tends to absorb and block X-rays, keeping them from coming down to the ground. This is wonderful for our health and for life on Earth, but again, it presents a challenge for X-ray astronomers. So every single X-ray telescope that we build must be sent into space as a satellite, or we would not capture any X-rays from the ground. In terms of the function of the telescopes, how they actually take their data, an optical telescope functions like a camera. It has a shutter that opens and exposes a detector with light for a certain amount of time. The shutter closes and the data is read out. So just like a camera. However, X-ray telescopes function differently and their detectors are built differently. The best analogy I can give here is that an X-ray telescope functions a little bit like a boarding agent at an airport. The airport boarding agent scans each individual ticket as you get on the plane. So at the end of the entire boarding process, a boarding agent can tell you where each individual person is sitting, how many people are on the plane total, and when each individual person boarded. We get lots of information when we count individual people getting on a plane. X-ray telescopes function in the same way. They count individual photons coming in, so we know where photons came from, we know when they came in, and we know how energetic they are. This is absolutely my favorite thing about X-rays and studying X-rays. It means that every single one of our data sets has multiple types of data products that we can use because we know spatial information, we know time information, and we know energy information. This is a lot harder to get with your classical optical telescope because it is possible to take an image of the night sky and get a picture, or it's possible to get a spectrum to divide the wavelength or the light up by wavelength. But you have to make this decision before you take the observation and insert specialized equipment into the telescope to do either one of these things. You don't have to make that kind of decision with an X-ray telescope. You can simply take your data and then decide afterwards what you want to do with it. Here's an example of the 3 different data products that we can get from every single X-ray observation. On the left, if we bin by position, this is saying I'm going to bin by where these photons came in, and I bin by X and Y. This gives me an image. And here is an X-ray image of a neutron star. It just looks like a very bright point source. That's because it's very far away and we can't quite see it resolved. We don't have that technology yet. In the middle, if we bin by the number of photons coming in and their intensity as a function of energy, then we get a spectrum. This is telling us about how many high energy versus how many low energy photons are coming into our telescope. And finally, on the right, we can bin by time. We can just ask how many photons are entering the telescope as a function of time over the course of your observation, which could be anywhere from a few minutes to a few hours. And in this case, this light curve shown here, the source is holding mostly steady. There's a little bit of noise, a little bit of chatter, but it's really not changing very much over the course of this observation. So let's imagine now that we look at one of these X-ray lighthouses. Here I'm using this demo image from the simulation video before. If I were to point 2 telescopes at this neutron star, such as the low energy telescope XMM Newton and the high energy telescope NuSTAR, I would be able to extract a total X-ray spectrum that included both low energy data from XMM Newton and high energy data from NuSTAR, giving a holistic picture of the entire X-ray spectrum of this source. If I were to look as a function of time, I might be able to see this source doing its rotation and actually capture the X-ray pulsations. Let's take a look here. Again, if NuSTAR is observing this neutron star rotate around, every single time the neutron star points its axis towards Earth, we see a higher number of photons coming in because we're looking right down that really bright X-ray beam. Every time that beam rotates away, we see fewer photons coming in. So our light curve, our brightness as a function of time, is actually made up of a lot of little pulsations as we observe the rotation of this neutron star. So if we see the pulsations as a function of time, we can determine how often the neutron star is rotating. Said another way, how long it takes the neutron star to rotate once. This is called the rotation period of the neutron star. And in many sources, it's about a second, a little less than a second, or just a couple seconds. They're rotating very, very quickly. We can actually then take our entire light curve, which is comprised of all of these very short little pulsations, and stack it up so that all the pulsations overlap. That's what's actually shown here in this image. This is not truly a light curve. This is a data product called a pulse profile, where I have taken the entire light curve, broken it up into individual pulsations, and then added all of those pulsations on top of each other. Why would I want to do something like that? Well, it gives me the overall shape of the pulses as seen from the telescope over the course of my observations. And we get a lot of information about the structure of the system by looking at the shape of these pulsations. The x-axis here is called spin phase. This is essentially time divided by that rotation period. So between 0 and 1, the neutron star rotates once completely. And I've plotted it twice so that it's a little bit clearer and goes from 0 to 2. And I'm going to talk about now in the next part of my talk, how we actually use a product like this to understand what's happening to the gas in the accretion disk. As a reminder from where we've come, we've already covered a lot of ground. We've learned that neutron stars form in X-ray binaries and that they get gas falling into their magnetic fields from their stellar companions so that we can study the gas interacting with these strong magnetic fields. The gas forms these accretion streams when it hits the magnetic field of the neutron star, and it's the rotation of these streams that give rise to pulsations, which we can detect in the X-rays. And we want to learn about the physical properties of the system by studying the shape of these pulsations, by studying the gas that's trapped in these ultra-strong magnetic fields. And so that is exactly what I'm going to do. I'm going to use emission from pulsars. Pulsars is a nickname that we give to pulsating neutron stars to learn about the shape of gas in their accretion disks. So where can we do this? What objects in the universe can we use to study these types of systems? The ideal laboratory is a neutron star that has a warped accretion disk. So this image is a very zoomed out view. The neutron star and its magnetic field would be within the dark point in the center. But that beam of radiation, the one that we pick up as our rotating lighthouse beam, is so powerful that it actually pushes on the accretion disk, and this can induce a warp in the disk itself, so that the disk is no longer a perfectly flat disk. It's actually raised on one end and lowered on the other, just from the strength of the neutron star's emission. These are ideal laboratories for studying what happens to gas in the accretion disk. And it's because we can easily find them. They have a very unique observational signature. So this is a video. The top panel is going to show a warped accretion disk, that's the gray and black lines, rotating around a neutron star, that's the small blue point at the center. The bottom panel is the overall brightness that an observer would see as a function of time if they looked at this system. And remember, all of the gas in this accretion disk is still spiraling in, falling towards the neutron star. So what happens is that the entire disk starts to rotate, and sometimes the disk blocks the neutron star from view. When this happens, we see less emission from the neutron star. It's screened, it's obscured, so the brightness goes down. And sometimes the disk rotates and the disk is out of the way. So at these times, we see much more brightness from the neutron star. We see direct emission. This is called a superorbital period, not named because it has any superpowers, but simply because it's longer than the orbital period in these systems. And it is a periodic increase and decrease in brightness over time that's caused by the warped accretion disk rotating into and out of our line of sight, and sometimes blocking the neutron star from our view, and sometimes moving out of the way. We see this in astronomical sources like LMCX4. LMCX4 is a neutron star that shows a superorbital period. The black data in this light curve, remember that's brightness as a function of time, is taken over 13 years, and it has been fit with a pink line that is a 30-day sinusoidal variation. So 30-day process of getting brighter to a maximum brightness and then getting fainter to a minimum brightness. This is the rotation period of the warped accretion disk around LMCX4, and it can be stable on the order of decades and even longer. Some sources are not as stable as this, but LMCX4 is a very stable source. Why are we interested in observing sources like this? Well, when we observe a warped disk, the observer is actually getting two signals, and this is really important. The observer is seeing direct emission from the neutron star or pulsar beam. This is that lighthouse beam shining directly towards us. So we get all of this really high energy emission coming straight out of the accretion column of the neutron star. But because the disk is warped, that same beam, as it spins around and the neutron star rotates, shines on the accretion disk, and the accretion disk absorbs some of that incoming radiation and then re-emits lower energy X-rays. This is a phenomenon called reprocessing, when gas is hit by high energy radiation and then re-emits lower energy radiation in response. So our observer in these warp disk systems sees high energy emission directly from the neutron star, from the pulsar itself, and low energy emission coming from this part of the accretion disk that is being illuminated by the neutron star. If we were to observe with two telescopes like XMM Newton and NuSTAR that specialize in high energy and low energy X-ray coverage, we can actually now disentangle these systems. So this is a real spectrum of LMCX4 shown on the left here, where the red data comes from XMM Newton and the blue data comes from NuSTAR. And we're seeing both emission from the accretion disk that's being blasted by this neutron star beam and emission from the neutron star beam itself directly. Because we can see this illuminated side of the disk and the disk is rotating, we expect the illuminated region to change over time. This is a couple screenshots from the video I showed before of the simulated disk moving around. And the areas that I've highlighted in yellow are the parts of the disk that would be illuminated by the neutron star at this given point in the rotation of the disk. And you can see that the yellow region is changing in size and it's changing in shape with time as the disk rotates. This yellow region is the part of the disk that is going to be doing the reprocessing of emission from the neutron star. And so this part of the disk is going to emit a pulse profile, the pulsations over time, but in low energies. And that low energy pulse profile will show changes over the course of this rotation period because the size and shape and geometry is changing as well. So this sets up the basis of the project that I started to do, or that I have done with LMCX4 and several other neutron stars that show this behavior. I set out to observe these sources at least 4 times over the course of a single superorbital cycle. That means one precession time of the disk. And these observations were very carefully timed so that observation 1 and observation 4 took place at the same point. The disk should have rotated fully back into its exact same configuration. And I want to look at the high energy pulses coming directly from the neutron star beam and the low energy pulses coming from the disk and look for differences between the two over the course of these 4 observations. When I actually do this data analysis, that's exactly what we see. Here are the 4 different panels of pulse profiles that came out of these observations of LMCX4. The blue curves are the high energy pulse profiles as seen by NuSTAR. The red curves are the low energy pulse profiles as seen by XMM Newton. And I can immediately here see that the disk is moving as we expect. In observations 1 and 2, the red and the blue curves are almost completely out of phase with one another, meaning that one is peaking when the other is at its minimum. But by observation 3, they've moved almost completely in phase. They're peaking at the same time and they're at a minimum at the same time. Well, almost. And by observation 4, we've moved back out of phase, peaking when the other is minimum. This is the evidence that we needed to actually observationally see the rotation of this accretion disk, the precession cycle of a disk moving around a neutron star. And now that I had this information, I could try to recreate this with a simple model. So I have the code from my thesis advisor, Ryan Hickox, that he started and I continued to recreate these pulse profiles. I have a fake disk that is built into the code with parameters that I can control, like how tilted and how warped and how big it is. And I have a fake neutron star that I can control its parameters, such as where the beams are, where they're located on the neutron star, and how big these beams of emission are. When I run my code, the neutron star rotates and it shines on the accretion disk, and the accretion disk precesses, and the code produces the pulse profiles that I would observe from that specific configuration. And that's what's shown matching up with our real data in these plots in the black curves. The black solid and dotted curves are my simulated profiles from the neutron star and from the accretion disk. And we see that with only a few exceptions, they're matching our data quite well. This means if I have successfully matched and produced a fake disk and a fake neutron star, simulated ones, that match our observed data, this is a possible configuration for the real accretion disk in LMCX4. So to review, we had 4 observations of LMCX4 at different points in its superorbital period. We expected that this would give rise to changes in the pulse profiles because the visible portion, the illuminated portion of the accretion disk was changing as it rotated. And we did see such changes in the pulse profiles. We were able to use our pulse profiles as inputs to model what this simulated disk might look like and recover out images of what the accretion disk around LMCX4 looks like during its precession. So these 4 images on the bottom are the outputs of my model, the actual configurations in terms of size of the accretion disk and angle of the tilt that reproduced our pulse profiles. These are potential snapshots of the gas trapped in these extreme magnetic fields. So this has been a thrust of a lot of my research, using a neutron star's low energy pulse profiles and high energy pulse profiles to model the shape of gas in the accretion disk, to actually map out what that gas looks like. And understanding the movement of this gas, the shape that it takes, and how it interacts with these strong magnetic fields will help us better understand these extreme environments and how it interacts with regular matter. I do have some exciting ideas about where we can go next with this research. We might be able to use this type of research, this method, to understand some of the most mysterious and extreme neutron stars that exist. These are called ultraluminous neutron stars. Now, an ultraluminous X-ray source might sound really fancy, but it's actually just a classification of how bright an X-ray source is. Typical neutron stars have a typical brightness of about 10 to the 36 to 10 to the 38 ergs per second, where erg is a unit of energy and second is a unit of time. So this is how much energy they're putting off as a function of time. And that's kind of on the lower energy scale for X-ray objects. At the higher energy scale, 10 to the 44 to 10 to the 46 ergs per second, we have supermassive black holes that live at the centers of galaxies. These are even bigger, they're more energetic, and so they tend to be brighter. Everything in between this range, 38 ergs per 10 to the 38 ergs per second to 10 to the 44 ergs per second, is called an ultraluminous X-ray source. And astronomers have thought for a very long time that these are black holes. Why did we think that they are black holes? Well, this has to do with something called the Eddington luminosity. This essentially means that the mass of an object, how heavy it is, determines how brightly it can shine. This is based on the idea that if a large object, here in my diagram, big M, is accreting a small gas cloud, little m, shown in the diagram, then at the very least, the gravitational force pulling the gas cloud towards the large object must be larger than the radiation pressure. Radiation pressure is the force of light that would be trying to disperse this gas cloud and blow it away. And if I set these two equations equal to each other, the gravitational force on the right and the radiation pressure force on the left, and solve for L, the luminosity, how bright this source is, what I get out is a function of several constants and big M, the mass of the object that is pulling things towards it. This tells us that how bright an object is determined by how massive it is. And we thought that the ultraluminous X-ray sources all had to be black holes because when we solved this equation, putting in their luminosities and solving for their masses, the masses that were coming out were hundreds to thousands of times the mass of the sun. And as I said on my second or third slide, a typical neutron star only weighs 1.5 times the mass of the sun. Only black holes can be this massive, so we thought all of the ultraluminous X-ray sources have to be black holes. But in 2014, Matteo Becchetti and other amazing scientists found X-ray pulsations coming from an ultraluminous X-ray source called M82X2, shown in this figure. The fact that we saw pulsations from this source means that it had a strong magnetic field rotating around, creating that lighthouse effect that we talked about with neutron stars. Black holes have no magnetic field at all. They're not magnetically active, and they cannot create X-ray pulsations. Only neutron stars can do that. So the fact that we found a neutron star that is thousands of times brighter than it should be means that we have some big holes in our understanding of accretion physics and how the magnetic fields are driving accretion in these sources. Since the 2014 discovery of this first ultraluminous X-ray pulsar, about 10 more have been discovered. We discover about 1 per year. And the more of these we discover, the more X-ray astronomers are asking, is this kind of accretion where an object is pulling in so much gas that it's shining hundreds to thousands of times brighter than our understanding of physics says it should? Is this extreme event actually commonplace? Is this how the world works and we don't understand it? Well, if we have an accreting neutron star, then we can do exactly the method that I just walked through using the high energy and low energy pulsations to model the accretion disk. And this might tell us if these sources are capable of sustaining an accretion disk, if they form an accretion disk at all, if their accretion disks have different shapes than the accretion disks that we're used to in our more typical sources like LMCX4. So this will be an important test using the pulse profiles to test if disk precession can recreate the observed pulse profiles from these extreme sources. It is an important way to shed light on some of the most extreme and extremely bright neutron stars that we know of in the universe. So I'm very excited to try this out in the near future and see if we can shed a little bit more light on these extremely unusual accreting neutron stars. That's all I have for you today. Thanks very much for your attention. I'd be happy to take any questions.
Dr. Brumback, thank you so much for that very expansive presentation.
We covered a lot of ground.
We did, and I feel like I learned so much, and I know that I have questions brewing and bubbling, but I'd just like to reiterate to everyone in attendance this evening that if you have any questions, any points that you'd like clarified, or even just some thoughts you'd like to share with us, please don't hesitate to pop that in the Q&A or in the chat function at the bottom of your screen. And while we wait to see if anyone brews and stews in spooky season for any
I'm happy to take questions on the research or on my career path or anything like that.
Amazing. Well, while we wait for them, I'm going to ask a question.
Okay.
How, or I guess maybe how and when did we determine that iron was the turning point of production to consumption during the fusion of elements in the universe?
I'm not going to be able to give you an exact date of when, but this was a discovery made in the laboratory when trying to reproduce nuclear fusion. We've been trying to reproduce fusion for ages because if we can nail it, it would be a very clean source of nuclear energy. All our current nuclear energy plants use fission, which means we are taking an atom and dividing it up into lighter elements. Fusion takes lighter elements and makes heavier elements. This happens naturally at very high densities and very high temperatures, which are commonly found inside of stars. But those kinds of environments are hard to recreate on Earth, and we haven't been able to recreate them stably. But we can recreate them in very short bursts. This is what the Large Hadron Collider at CERN in Europe does. It smashes particles together and we get brief bursts of nuclear fusion. So through tests like that, and by studying the particles that come out of these types of reactions, we realized that when, I believe it's carbon, is fused into iron, the iron nucleus that comes out of this is actually heavier than the carbon nuclei that go in to create it. And this is the opposite of what's happened before. When we fuse hydrogen into helium, the helium atom that's created is lighter than the hydrogen atoms used to make it. And that energy, that mass lost, is converted directly into energy through Einstein's famous equation, E = mc squared. Mass is energy. So because when we fuse iron, we are now, we're creating more mass than we started with, this process requires energy to happen. It consumes energy. So it kind of eats up the energetic heart of our stars and leaves nothing left to support all of their weight, and they collapse into a supernova.
Oh, I was muted. Thank you for that. Where do you think this research will be in 50 to 100 years, and where will it take us? Kevin Barry, one of our listeners and viewers, had that question.
Oh, great question. Well, in 50 to 100 years, I very much hope that we are building more powerful X-ray telescopes that maybe let us do some direct imaging of these objects. Direct imaging, I mean, actually take a picture that we can resolve, just like this picture. This is an artist's rendition on this slide of a neutron star within its accretion disk. We currently don't have telescopes powerful enough to see objects that are this small and this far away. But as our technology develops, we might be able to actually image these objects directly, and that will tell us so much about the gas in the magnetic fields and how it's moving and how it's behaving. That would be really exciting. In the more immediate future, just in September, a joint NASA and JAXA, so the Japanese Space Agency, launched a mission called XRISM. XRISM is an amazing new X-ray telescope that does not image in high resolution, but it takes spectra in high resolution. So all of the spectra from XMM Newton and NuSTAR that I showed are very low resolution spectra. There's not lots of fine features in there. XRISM is going to look at the fine features of an X-ray spectrum, and this is really important. It tells us individually about the gas that's in these accretion disks. We can pick out individual excitation lines of oxygen and iron and really start to understand the chemical composition of the gas in the accretion disk. So XRISM, having just launched, it's still going through its calibration phases now, but within the next year, it should be available to do astronomical science. I have a lot of projects in mind for XRISM coming up in the near future.
So tell us what led you to this body and field of work.
Well, when I started out in graduate school, I will admit I didn't necessarily enter graduate school thinking, oh, I would like to be an X-ray astronomer and I want to study neutron stars. I was very interested in space, and I was really open to trying a lot of different things. I really liked the way that Dartmouth arranged its graduate program for astronomy students. It had me in my first year try a one-year research project with a faculty member. All the faculty members kind of presented these short little projects, and I got to choose the one that was most interesting to me. I actually did a project on supernova remnants, but using optical data from Hubble. And it was a really interesting project, but I found that I was just mostly drawn to the energetic processes going on behind the supernova, more so than I was the images of the remnant. So this led me to work in Professor Ryan Hickox's research group. And Ryan does research on two supermassive black holes. So he is a proficient X-ray astronomer, and used to kind of hunting for these supermassive black holes at the centers of galaxies. And I really liked X-ray astronomy. I was very interested in X-ray detectors and how they worked and the types of science we could do. But I'll admit, when he was talking about supermassive black holes, I was like, this is interesting, but I don't know if it's quite what I'm interested in. And Ryan was gracious enough to pull out an old project for me. This was something that he had started in graduate school and hadn't quite finished. And this kind of evolved into the research I presented today, using X-rays to study the gas around neutron stars. So the process of finding my own research path was one of taking advantage of the research around me at graduate school from all the different professors and really following my gut with the areas I found most interesting. And I really don't regret any of these decisions, even though I, essentially did my thesis in a project that was not my thesis advisor's main research focus. I love what I do so much, and I'm just so grateful that I had the opportunity to pursue neutron stars.
Thank you for sharing that with us. I guess my follow-up question would be, what, in your opinion, and professional, of course, what effect has X-ray probing made on the field of astronomy?
That's a great question. Well, this technique that I've showed about using different energy X-rays and using the pulse profiles has a more generic name, which is called reverberation mapping. And we're essentially using, these pulsations to map out the structure around gas. We also do this with black holes. And black holes are much more challenging to study than neutron stars because they are so gravitationally intense that they have this event horizon where light cannot escape. We cannot study the surface of a black hole directly the way we can with a neutron star. So reverberation mapping techniques, where we're using different signals and timing when we receive pulsations or vibrations from different wave bands, different energy bands around black holes, is really the primary way to study the structure of black holes and how material falls onto them, and to kind of see through the event horizon without really being able to see through it. So I'd say that probably some of the most significant discoveries in X-ray pulse profile mapping and reverberation mapping have been done around black holes, particularly work done by Andy Fabian and Javier Garcia in mapping what makes black holes so energetic, from where are they shining, and what the structure of gas around black holes looks like.
How can amateur astronomers aid or support your work and the work that's done by everyone in your field?
Well, specifically my research, this is not necessarily in my wheelhouse, but amateur astronomers or interested citizen scientists can always look up citizen scientist projects. There's a lot of very interesting citizen scientist projects out there, and they're usually things that have so much data to look through that astronomers can never get it all done. They need help, essentially. And so I know of several interesting citizen scientist projects. One is classifying galaxies taken with pictures from Hubble, and you look through and you ask yourself, is this an elliptical galaxy or a spiral galaxy? And you're helping the actual astronomers sort through their data. It's really important. That's not so much my own research area, but it's a great way for interested citizens and citizen scientists and amateur astronomers to get involved. The other best way, I think, for anyone to support and advocate for scientific work is to continue to advocate for it to any of your local politicians, to continue to be involved with any local science committees like the Maria Mitchell Association. These kinds of associations continue to tell Congress that NASA is very important and the work of astronomers is very important. And, whenever we launch new telescopes, whether they be X-ray telescopes or any other wavelength, we are literally able to peer farther into space and see things that have never been seen before. But that takes money. And the money comes from Congress in the congressional budgets that go to NASA. And there's a lot of really, really other compelling things in the country that take up a lot of money. So the best way to advocate for science and keep science going is to continuously invest, either politically or through local science agencies, into science, so that Congress understands that this work and understanding the universe and our place in it and understanding the physics that governs our entire planet is really important work.
Duly noted. What advice would you have for any young and budding scientists who are interested in astronomy, interested in physics, even in chemistry? What would be your most sound advice to them?
Ooh. My sound advice is that if you're interested in science, be it astronomy or physics or chemistry, do not be overly intimidated by the mathematics of all of it. Science and STEM fields inherently come with a lot of math, and it can be very intimidating, especially for women, for underrepresented minorities in science classrooms. It can be harder to gain some of those mathematical skills. I've felt the impact of that myself. If you had talked to me as a middle schooler and said, "You're going to be a physicist," I would have laughed, because I thought, I can't do a math related field. That's too much. I'm not good enough at math to do something like that. But the reality is that most of the math that we're doing now, we're not writing out calculations. I mean, I do that sometimes. It depends on the work, but we use computers to do a lot of the heavy weight lifting for us. So if you're at all interested in math and science, you can do it. You do not have to be Albert Einstein at the chalkboard coming up with incredible theories in order to be an astronomer and to make contributions to this scientific field. And if you're at all interested, I suggest checking out computer programming, learning a computer programming language. There's plenty of free resources on the internet to help you pick up Python. There's summer programming camps to help you learn Python. So much of astronomy is at its heart data analysis, and that means knowing coding in some kind of language. And that's helpful not just in astronomy, but in a whole slew of fields. So if you think this is something you're interested in, try your hand at programming. Try something fun, code up a little calculator, make your computer say hello world to you, and that will start building you up the building blocks of being an astronomer. And it's honestly much more important than being some kind of mathematical genius.
Mm-hmm. So how would you propose, or might you suggest, that we shift that cultural narrative in education to help foster and build confidence in young, interested and budding scientists? Just because for instance, in my high school classrooms, a lot of kids would come to me and say, I'm just not a math person, I'm just not a science person. And it's something that they've heard their entire academic journey so far. And shifting that cultural narrative, I found to be the root of my work. To take the education aside, how do I get these kids to really believe in themselves? So what would you suggest that us as educators, paraeducators, and parallel educators, that we can continue to do to shift that narrative?
Oh, absolutely. I think about this a lot as a professor. How can I instill confidence, quantitative confidence in students who have been repeatedly having negative experiences in math classes? And it can be really, really hard. There are a couple techniques that I'm implying in my classrooms, although I am constantly trying to learn more about this to make my teaching as effective as possible. The class I'm teaching this semester is open to any major, any class year. So we have this huge range of students with ranges of comfort levels with math. I like to get the students doing hands-on activities as much as possible, because nothing is worse than watching your professor do some kind of complicated math derivation on the board and you're not following it and you're not paying attention, and then you're checking your phone. You don't, it's just natural to kind of step away from watching someone solve problems on the board.
Right.
There's a time and place for that. It is important, but it should not be the only thing, the only way we learn. So in my classroom, I have students do group packets, probably at least once a week. I try for once a class, but usually once a week, where they're not so much doing math with numbers. We're thinking more qualitatively. If I increase the radius of a star, does that mean that it gets hotter, or does that mean that it gets brighter? Those kinds of questions. Those are at their heart math questions. There are formulas that they're learning that govern those kinds of things, but we don't have to ask them as math questions. We can ask them as reasoning questions. And so I have the students work in small groups together on packets like that. I also place a really huge emphasis on highlighting diverse scientists and recent discoveries from a diverse pool of scientists in my coursework. So, for example, my students are just starting the unit on stars in general, classifications of different types of stars. And this work was famously done by a group of female astronomers who were just given what was deemed as kind of the work at Harvard in the early days of astronomy. But Cecilia Payne-Gaposchkin and Annie Jump Cannon were some of the first women classifying the stars in these systems. And I will be highlighting the contributions of these women who are, just as important and significant to the field, along with all the names that get mentioned in every single astronomy classroom, like Newton and Einstein and Kepler and Brahe. They're all super important, but there are our white men class, and we have to highlight and show students, no matter what background you come from, you can also be a scientist. Look here, other people have done it too. And I find that really empowering by providing students with role models and examples of how science has been contributed to from such a diverse range of scientists.
I'm really happy that you said that, because I think that that is such an important facet of education that I find to sometimes be lacking in high school classrooms. And it's not for lack of effort by educators. I think that the system is just designed in a way that we feed the information that is just readily available, and teaching students to critically think outside of the box and also to develop and strengthen their deductive reasoning skills has been a journey, to say the least.
Absolutely. It takes work, and there's obviously, pressures in both directions. We've got a curriculum to get through. We need to get from A to B. We only have a few weeks to get there, but we can do it. It just takes a little bit of effort and encouraging our students, noticing when they're struggling, really meeting with them. And this is why I am so excited to have ended up at a school like Middlebury, where I can spend the time engaging with my students individually and not letting anybody get too overwhelmed or too behind by the math we're doing.
It makes me want to take your class.
Thank you.
I guess I have one more question, or two more actually, and this is just my braining. How is it, or how does a star in binary survive its companion going supernova?
A great question. Yes, because when we have these binary systems, one star has dramatically blown up and the other still remains. Stars that are more massive tend to burn through their nuclear fuel faster. So whichever star in the binary is larger to begin with is the one that's going to go supernova first. And this explosion can, in the right conditions, if they're close enough, destroy the other star. And then we would not have a binary system. We would just have a little neutron star or black hole by itself as the other star fades away. But usually the radii in these binaries are large enough that even if the explosion strips away some of the outer layers of the star, it still remains intact. A star is a very big object, and so even with an explosion as violent as a supernova, it can still survive that, essentially. It might lose a few outer layers of gas, but it won't be completely stripped by the supernova explosion. It's also, in theory, possible for a supernova to happen with a star, either in a binary or by itself, and have the neutron star that's left behind get some kind of kick in one direction and actually be kind of sent off through space in that situation, it is possible for a star that was not originally in the binary to kind of catch the neutron star and they end up in a binary orbit together. That's much more rare. We don't think that happens as much as the binary evolving together, but it is possible.
Well, thank you. Now I can sleep tonight.
Yes, it's all right. These stars are weathering their companions' supernova explosions just fine.
What question do you wish that I had asked you thus far?
Ooh, we've asked very good questions, so that is a tricky one. I guess one thing that's always fun to talk about is, well, even that you asked about, oh gosh. I was going to say the fun thing to ask about is like new upcoming science, and then I would talk about CRISM, but I already talked about CRISM. I guess one thing that you could have asked is a way in which maybe student scientists can involve any students who are looking to apply to colleges and thinking maybe I want to look into astronomy, like what are some things to look for? I would say that a growing number of colleges of all sizes, from big state schools to small liberal art colleges, are investing in astronomy. So look for schools that have telescopes or have purchased time on larger telescopes. Both of these things are incredibly common, either purchasing time on telescopes or having telescopes yourself. And check within the physics department. If a school is small enough, it might not have a separate physics or astronomy department. It might be a joint department or even just a physics department in which many astronomers live. So don't be afraid or scared away by the word physics and physics department. Go look and see. The astronomers are often living within the physics departments, and there's lots of fun ways for schools with these resources to involve their students in research. If a school, a larger school, like I know the University of Michigan, partially owns a telescope outside of Tucson, Arizona, they send their undergraduate researchers to that telescope to actually do research and take data with the telescope, which is so exciting. And at Middlebury, obviously a much smaller institution than the University of Michigan, we have a little telescope on the roof. It's great. It's small in size, but very powerful. And the students in my class this semester are actually using it to take images of nearby galaxies as one of their laboratory assignments throughout the semester. So there's awesome ways as just a student in college to get involved in astronomy and to try this out to see if you like it. So I'd say if you're at a school or looking for a school, look for those opportunities. They exist, and come try out astronomy. It's very fun.
I love that. Well, thank you for answering the question that you asked. With that, I'd just like to say thank you again so much, Dr. Brumback. It has been such a fascinating journey venturing through the cosmos with you this evening, as well as having these broad and wonderful conversations as to how we can all participate in advancing the astronomy field. Is there any advice or any words you'd like to leave us with this evening?
I will just say, first of all, thank you. It's been an honor to come speak with you and share my research. And so I very much appreciate the opportunity. And it's been a pleasure working with you all the way through. So thank you. And thank you to everybody who came and listened. I very much appreciate it. Final wisdom, I suppose, is just to look up and appreciate our night sky and our place in the universe. It's a vast unknown universe out there, and there are real people trying to piece together all the mysteries every day. It's an exciting time to be an astronomer and to be a citizen interested in astronomy. And for those of us in North America, don't miss the total solar eclipse in April. Not coming through Nantucket, unfortunately, but coming through the central part of the US. And try to go see it. It'll be awesome.
We are definitely looking forward to it. We're also wholeheartedly looking forward to see where the future brings you and takes you, as we hope to keep in touch with you.
Absolutely.
On behalf of the entire Murray Mitchell Association, it has been an absolute honor and pleasure to host you this evening. And I'd like to say a special thank you again to Bank of America, our lead sponsor, as well as Cisco Brewers of Nantucket and the White Elephant Hotels and Resorts, who make our Science Speaker series complimentary and accessible to all viewers and listeners. And just to keep fostering a love and interest for science, as well as learning by doing, which is the Murray Mitchell way. McKinley, it has been an honor, and if you'll hang back for a few seconds, I'll conclude our Science Speaker series this evening. Thank you again.
Thank you. Good night, everyone.
Good night, everyone.